Okay, now that we've talked about some factorizations and now that we've gotten an idea that in the future, in this course and in the present of internet security, large numbers are playing a big role, it's time to start thinking about how to actually put large numbers into a computer so that we can do arithmetic with large numbers. And in order to do that, we're going to introduce the fundamentals in this presentation, which is about arithmetic modulo m. And we're also going to talk a little bit about how that already can affect things like fast exponentiation and the details of arithmetic using using modulo m arithmetic through the Chinese remainder theorem will be done in the next presentation. Okay, so why is this modular arithmetic so important? Well, basically because it already occurs on computer chips. Let's take two numbers, and so here we have the number 106 in binary. Let's see, because that would be 64 plus 32 is 96, plus 8 is 104, plus 2 is 106, right? And we have the number 174 in binary. Well, 128 plus 32 is 160, plus 8 is 168, plus 4 is 172, plus 2 is 174. And, well, so in an 8-bit arithmetic, how would those two be added? Well, 0 plus 0 is 0. 1 plus 1 is 0 with a carryover of 1. 1 plus 1 is 0 with a carryover of 1. 1 plus 1 plus 1 is 1 with a carryover of 1. 1 plus 0 is 1 with no carryover. 1 plus 1 is 0 with a carryover of 1. 1 plus 1 is 0 with a carryover of 1. 1 plus 1 is 0. And now we've got a problem because in an 8-place arithmetic, we can only capture these 8 digits, and so that last carryover, as we go modulo 256, which is what an 8-place arithmetic would be, that last digit is being lost. That last carryover is gone. Now, however, if we look at the result here, the result should be, let's see, 16 plus 8 is 24, right? And 24 modulo 256 is 256 plus 24, which is 280. And 280 happens to be the sum of 106 and 174. So if this number here is A, and this number here is B, then A plus B is actually the following. If A is about here and B is about here, and I measured that out, that should be how much it takes from a circle where the circumference is 256. Well, then when we add A to B, we're wrapping around across m equals 0, but we're wrapping around in such a way that we get the right result, except that that we are off by one modulus. We're off by exactly 256. Okay, so there's A plus B. Well, so basically, computer arithmetics currently are modulo 2 to the 32, which would be a 9-place arithmetic, and well, yeah, that's what 2 to the 32 is. Or there are modulo 2 to the 64, which is a 19-place arithmetic, as long as you're working with what is called unsigned integers. And all computer arithmetics have the same problem, and that is because they have a limited number of digits, at some point in time, this wrapping around that we have seen on the previous panel, this problem that ultimately a carryover is getting lost, that happens in any of these limited place arithmetics. Okay, now on the other hand, we also have to realize that these numbers may look large, but internet encryption works with 100-place numbers routinely, or larger numbers even. So that means we need we need more places of precision. And the leading bit is often used for a plus or a minus sign, so that we could use negative numbers. And 2 digits, 6 or 7 bits, may also be used for an exponent, so we can express real numbers in, I guess that's called scientific notation. Well, no, scientific notation is where the exponents go with multiples of 3, I think, but basically in that we would express numbers in base 10 notation, where we take a decimal between 0 and 10 and multiply that with 10 raised to the appropriate exponent. Okay, so basically what that means, these overflows that we have seen on the previous panel in limited place arithmetic are just simply unavoidable. But we may be able to salvage just a little bit, because we've also seen on the previous panel that we were just off by 256, which was this modulus. And even if this modulus thingy here becomes a little bit more inconvenient, if we just know that we're going to be off by a multiple of a certain number, maybe we can do something. And so the definition of the congruence relation really hits upon exactly that point. You take m to be a natural number, that's the modulus, and we let x and y be integers. Then x and y are called congruent modulo m if and only if m divides y minus x. So that is the case if and only if there's an integer k, so that the difference between y and x is k times m. So that is congruence modulo m. Sometimes that is also called equivalence modulo m. And we're going to spend this presentation working on how to do arithmetic with these things. And when x and y are congruent modulo m, we will also write that x is equivalent to y modulo m. So this equivalence sign here is basically an equal sign with 3 dashes. And the number m, as I mentioned, is also called the modulus. We're just putting a complete definition down here. And then the first proposition is, if m is your modulus and x is an integer, then x is equivalent to d modulo m, where d is the remainder of the division of x by m. And that isn't even something that we have to prove, because what is the difference between x and its remainder? It's the quotient times the modulus, so that difference most certainly is divisible by m. Okay, as an example, just from daily life, when you tell time in hours and minutes, we already use implicitly congruence, because if you look at 75 minutes, well, that's 1 hour and 15 minutes, and 15 is equivalent to 75 modulo 60, because the difference is exactly 60, right? So when we're looking at 15, 75, 135, 195, and so on, they are all congruent modulo 60. And if you will, that is because if these were minutes, and the minute hand started in a 0 position, then the minute hand would always be in the same position after each of these time intervals had elapsed. That's why this modular arithmetic is also called clock arithmetic, for example, because we have the same kinds of wrap-arounds as we would have on the face of a clock. Okay, now if x is a set, then a relation equivalent, or tilde, contained in x cross x will be called an equivalence relation if and only if the relation is reflexive. That is, for every x element x, we have that x is related to itself. We have that tilde is symmetric. That is, for all x, y in x, we have that x tilde y is the same as y tilde x. And tilde is transitive, so that means that for all x, y in and z in the set x, x related to y and y related to z implies x related to z. Okay, now that is a complete shift of gears, it seems. All of a sudden we're talking about sets and relations. What's the idea here? Well, equivalence relations are sort of like equality, but not quite, because certainly equality is something where every element is equal to itself. Equality is so that when x is equal to y, then y is equal to x. And equality is also so that when x is equal to y and y is equal to z, then x is equal to z. But we're going to see that equivalence modulo m, we're going to prove that on the next panel, that also is an equivalence relation. And so basically what that means is that equivalence is very similar to equality, but it is just not quite equality, and that's going to be good enough to have all sorts of really nice consequences for us. Okay, so the proposition is, when m is a natural number, then congruence or equivalence modulo m is an equivalence relation on the integers. So the proof, reflexivity is quite trivial, right? Because x minus x is 0, and 0 is certainly divisible by m. For symmetry, take two integers and let them be so that x is equivalent to y modulo m. Well, then x minus y is a multiple of m. It's k times m for k in z. And that means that y minus x is negative k times m, and that means by definition that y is equivalent to x modulo m. And for transitivity, we would let x, y, and z be integers so that x is equivalent to y modulo m, and y is equivalent to z modulo m. Well, then x minus y is some number k1 times m. And z minus y is some number k2 times m for k1 and k2 in z, and that of course means that now z minus x is just z minus y minus x minus y, right? The old story that there's only one trick in mathematics, and that's adding 0. Well, maybe there are two tricks. You could also multiply by 1. But here we add 0 in the form minus y minus negative y. And now we realize that z minus y is k2m and x minus y is k1m. And that of course means that k1 minus k2m is equal to z minus x. And that means that m divides z minus x. And hence x is equivalent to z modulo m. Okay, so that means congruence modulo m is an equivalence relation. In a theory class, that would be certainly a jumping off point to use this as an example for equivalence relations, and now talk about what equivalence relations do. And one of the things that I don't think we'll mention explicitly here is that an equivalence relation basically cuts up the underlying set into disjoint classes. So for example, equivalence modulo m cuts up the integers into disjoint subsets of numbers that are all equivalent modulo m. And what you're then interested in is actually a complete set of representatives, or here a complete set of residues modulo m. And when our modulus is a natural number, then a set of integers a1 through ak is called a complete set of residues modulo m if and only if for every integer x there is a j, so that x is equivalent to aj modulo m. So that complete set of residues is a set of representative numbers, and so basically if we have one of those sets of representative numbers, then we basically control all the numbers because everything else is equivalent to one of those things. And as a quick theorem, when m is our modulus, then the numbers from 0 through m minus 1, that set is a complete set of residues modulo m. And the result is fairly quick, because when n is an integer, then by the division algorithm there is a d, well, I would want to call it q, so a quotient d, and a remainder r between 0 and m minus 1, so that n is equal to d times m plus r. And that of course means that the residue is equivalent to n modulo m, and that means we are done, because every integer is in fact represented by one of the numbers between 0 and m minus 1. If we now take a modulus m, we will claim that a set a1 through am of integers that are pairwise not congruent modulo m, and that just means that if I is not equal to j, then ai is not equivalent to aj modulo m, then that is a complete set of residues modulo m. So basically that means if we at some point in time leave the realm of just the numbers between 0 and m minus 1, as long as stuff stays pairwise distinct with respect to this new equivalent sign here, then we still have a complete set of residues modulo m. And the proof uses the pigeonhole principle, I think, because for every j by the division algorithm, there are dj being an integer and rj being a remainder between 0 and m minus 1, so that aj is djm plus rj. And because the aj's are pairwise not congruent modulo m, the rj's must be pairwise distinct, right? Because otherwise we would have an aj and an ai having the same remainder rj equals ri, and that would mean that the difference between aj and ai is divisible by m, because it would be dj minus di times m. So that means that the rj must be pairwise distinct, but that means that r1 through rm is a complete set of residues, and that means that a1 through am, which is a set of equivalent numbers, is also a complete set of residues modulo m, because basically these rj's are pairwise distinct, so they are the numbers 0 through m minus 1, because there are m of them, and they are between 0 and m minus 1, and each ai is equivalent to one of these numbers, which means because there are m of them, we get all of them, and so that means we have that every integer is equivalent to one of these numbers, and therefore also equivalent to one of these numbers. Okay, now we talk about well-definedness, and this is one of those things that again takes some time in a theory class also. But basically, congruence modulo m leads to the first natural example of an operation that is not obviously well defined. What do I mean by that? Basically, the question is, how do we know that when we add two different representations of two numbers modulo m, say 4 plus 7 and 9 plus 22, when we add those modulo 5, we realize 9 and 4 are equivalent modulo m, and 7 and 22 are equivalent modulo m. So how do we know that the sum 4 plus 7 is congruent modulo 5 to the sum of 9 plus 22? Basically, that is something that we would want to be true because, as I keep saying here, we want to do arithmetic modulo m, and that only works if our arithmetic operations play ball, right? And so that is then also important because wraparounds in computer arithmetic lead to this possibility. We would no longer get the right result in terms of the usual arithmetic, but we would get the right result modulo m if addition and multiplication are well defined in the above sense. And we're also going to state the results in the appropriate form. And with arithmetic that runs on a chip, that is of little use, of course, because you still lose carryover and you don't know how many carryovers you have in a multiplication, for example. But it does pave the way for the Chinese remainder theorem, which is used for arithmetic with large numbers. Okay, so basically for well-definedness, we need results of this kind. Let m be our modulus, and let a, b, c, and d be integers, so that a is equivalent to c, and b is equivalent to d, both modulo m. Then we claim that a plus b is equivalent to c plus d modulo m. So that means we may lose the carryovers, but at least these remainders that we have work in some fashion exactly. And the proof, well, you take a, b, c, and d, so that a is equivalent to c and b is equivalent to d. First thing you do is you write down what that means. So there's a k1, so that a minus c is k1m, and there's a k2, so that b minus d is k2m. And then you look at a plus b minus c plus d, because that's what you want to prove the equivalence for. Well, then you realize that that's a minus c plus b minus d. And that's, of course, k1m plus k2m, because we have this equation here and this equation here. And that means this is k1 plus k2m, and that's already it, because this means that m divides the difference between a plus b and c plus d, and that means a plus b is equivalent to c plus d modulo m. Okay, we also want to multiply, so we do the same thing over again. We take a modulus, we take a, b, c, d, so that a is equivalent to c, b is equivalent to d, both modulo our modulus m. Then a times b is equivalent to c times d modulo m. And, well, same story, right? We decode what it means. We first remind ourselves, okay, a, b, c, and d are so that a is equivalent to c, b is equivalent to d. We remind ourselves that that means that a minus c is k1m and b minus d is k2m. And now, well, now we have to look at ab minus cd. Well, we can't factor anything out here, but if we throw in a mixed factor, we have some hope, because if we now just subtract and add b times c. So, right, this old thing, there's only one, well, there's two tricks in math, adding 0 and multiplying by 1. We've added 0, and now we can factor a b out of the first two and a c out of the second two. So we get a minus c times b plus b minus d times c. And of course, the purpose here was that we wanted to get terms a minus c and b minus d. And we have those now. And so the first one now is k1mb, and the second one is k2mc. And that means that ab is equivalent to cd modulo m, because m divides both summands here, which means m divides the right-hand side, and that means m divides the left-hand side. Okay, and now we can start thinking about arithmetic with congruence classes. So basically, and here's where in this class we're not going to talk about that much about congruence classes, but we could say if a sub m and b sub m are the congruence classes modulo m of a and b. So this is the set of all the numbers that are equivalent to a modulo m, and this is the set of all the numbers that are equivalent to b modulo m. Well, then, if a is equivalent to another, is equal to another congruence class c, and b is equal to another congruence class d, then we could actually say that the equivalence class of A plus B is equal to the equivalence class of C plus D, and the equivalence class of A times B is equal to the equivalence class of C times D. So basically, if we work with sets of numbers, then this arithmetic now is actually something where we have an arithmetic for sets in which equality works just fine. In other words, yeah, addition and multiplication of congruence classes by adding and multiplying representatives, that is a well-defined operation here. Okay, well, now we're going to add, subtract, well, we're going to add and multiply. Subtracting shouldn't be too bad once we have worked out what negative numbers are, which, well, actually, in modular arithmetic, we're not going to mess with subtraction that much, and if we do, we just subtract the integers and then go back to the right representative. Multiplication is a little bit more interesting because, well, one of the things we know about integers is that in integers we can't divide, and it turns out that in modular arithmetic, under the right circumstances, we will be able to cancel, we will be able to divide. So let m be our modulus. As always, we take three integers a, b, and c. We let d be the greatest common divisor of c and m, which in particular means that we're assuming that c is not equal to 0. And we assume that ac is equal to bc. And of course, the thing that we really want to do is we want to conclude then that a is equal to b. And in integers, well, we don't formally divide, but there's a cancellation law that we can use, or we would simply briefly jump and embed the integers into the real numbers. Well, in modular arithmetic, we can't really do that because modular arithmetic, even though the numbers are still denoted with the same symbols as for real numbers, the numbers now work differently, right? Because they're wrapping around, whereas real numbers don't. So taking AC equivalents BC and concluding from that that A is equivalent to B now is no longer something that is quite trivial. And what we can conclude is not that A is equivalent to B modulo M, but we will conclude that AB is equivalent modulo M divided by D. Okay, that doesn't highlight too well. And well, how do we prove that? Okay, so without loss of generality, we can certainly assume that C is a number between 1 and m minus 1 because it's not 0 and it's an integer modulo m, so we could use the right representative here to work things out. And we can suppose for a contradiction that A is not equivalent to B modulo m divided by D. Well, that means that there is an integer k and a remainder between 1 and m over d minus 1, and it's important that r has to be small in some way, so it has to be smaller than m over d. Well, that has to exist so that b minus a is equal to k times m over d plus r, right? So the division of b minus a by m over d does not give us a remainder 0. That's what it means for a to be not congruent to b modulo m over d. Okay, but then, well, let's take a look at bc minus ac. Well, that's b minus a times c, and we know what b minus a is, so this is k times m over d plus r, and c is, of course, d times c over d, and now we're just going to multiply that out. So that gives us km over d, dc over d, so that's kmc over d, plus rdc over d. And that is problematic now because the first one is divisible by m, because remember d is a divisor of c, so c over d is really a number, an integer. And so the first one is divisible by m, and the second one is not. So because m divides bc minus ac, and because m is also a factor here, we have that m divides rd times c over d, and that is now problematic because this is r times c, and r is between 1 and m over d minus 1, and c is between 1 and m, and so that means by definition of d and m. Okay, so I was trying to say that this product is smaller than m, but that doesn't work out, so let's see. By definition of d, comma, m and c over d have no common prime factors. Right. Yeah, that's because c over d is c divided by the common factors there. And so that would mean now that m divides r times d, right? Because if m has no common factors with c over d, then m must divide r times d. And that is not possible because r times d is smaller than m, right? Okay, I jumped the gun here a little bit. I wanted to go with r times c. I have to go with r times d, and that's because r is smaller than m over d minus 1, so r times d is smaller than m, and that means that m cannot divide that number, especially because r times d is also greater than 0. Okay, so that means as long as we are willing to switch the modulus, we can have a cancellation law. It turns out that otherwise there is no such cancellation law, but that'll be just fine because the main corollary that we really are interested in is that if m is our modulus and a, b, and c are integers, so that the greatest common divisor of c and m is equal to 1, forget the let, that's just not there, and I'm not going to correct it right now. If ac is equivalent to bc modulo m, then a is equivalent to b modulo m. And that's, of course, very quick because it's just the previous theorem with d equals 1. Now, something that I don't think I have examples for here, and that's something that I want you to think about, is if the greatest common divisor of c and m is not 1, then it actually turns out that there will always be numbers a and b for which the cancellation law does not hold. That's a really good exercise. Work that through with arithmetic, modulo 4, modulo 6, modulo 9, and so on. The one thing that you can't do is you can't work that example through with arithmetics that are modulo prime numbers, and those will really be the important arithmetics for us. So if p is a prime number and ab are integers, then if ab is equal to 0 modulo this prime number p, then a is equal to 0 modulo p, or b is equal to 0. Okay, that's something that I have to fix. Give me a second here. Okay, we're back. So we are concluding that a is equivalent to 0 or b is equivalent to 0 modulo p, and that is because, well, either b really is equal to 0 already, or I can cancel b with the cancellation law that we've got up here, and then a would be equal to 0. So basically what that means is that in prime modulus arithmetic, we have the usual factorization laws, and we also have the cancellation law, of course, because when if m is a prime number, then anything has greatest common divisor 1 with our prime modulus except for 0. So arithmetic modulo prime numbers is an arithmetic with integers that allows us to literally do division, and we have multiplicative inverses and things like that. So I think that's that's sort of the next one here. So if we take a modulus and we take a complete set of residues, modulo m, and we let a, b be integers so that the greatest common divisor of a and m is 1, then ar1 plus b through arm plus b is a complete set of residues modulo m. How does that go? Well, for I not equal to j, we have ari plus b minus arj plus b is just a times ri minus rj, and realize that because am equals 1, we can cancel the a, right? So that is not equal to 0 modulo m, because ri minus rj is not equal to 0 modulo m, and a is also not equal to 0 modulo m, so that means that their product is not equal to 0 modulo m, because otherwise one of the factors would be equal to 0 modulo m, because we would use the corollary up here. And by an earlier lemma, namely that if you have m pairwise distinct numbers modulo m, then we have that these things are a complete set of residues modulo m. Okay, well, so now we're starting to move towards modular exponentiation. Let m and k be natural numbers, and let a, b be integers so that a is equal to b modulo m. Well, then a to the k is equivalent to b to the k modulo m. And the proof is fairly simple. We do an induction on k. The base step k equals 2 was already proved earlier. And if we take the induction step from k to k plus 1, we note that a to the k plus 1 is, of course, a to the k times a, which is b to the k times b, because a to the k is equivalent to ab to the k, and a is equivalent to b, and that's b to the k plus 1. And that's all modulo m. Note that in the middle, even though it is very tempting and often happens that I will say equal rather than equivalent modulo m, it's all in equivalence modulo m here. Okay, and that concludes the proof that exponentiation or powers are well defined. And well, we just keep building lemmas actually. So for integers m1 through mk, we don't denote their least common multiple by bracket m1 through mk. And if you have m1 through mk that all act as moduli, and if a is equivalent to b modulo mj for all j, then a is equivalent to b modulo the lowest common multiple of m1 through mk. That is something that we will actually need for the Chinese remainder theorem, which we'll talk about in the next presentation. So as a proof, well, because a is equivalent to b modulo mj for all j, the difference b minus a must be a multiple of all of those mj, and that means it must be a multiple of their lowest common multiple, and that means a is equivalent to b modulo the lowest common multiple of m1 through mk. And now we're going to talk quickly about fast modular exponentiation. And well, the need for fast operations is founded in the fact that, for example, internet encryption requires arithmetic with large numbers. And so on one hand, we must set up the arithmetic to avoid the wraparounds that we talked about at the start, right? I mean, right now, as it stands, never mind fast, we'd like to just have some arithmetic that's accurate. But the Chinese remainder theorem will do that. And so as soon as we can work with these numbers, we also want to work with these numbers as quickly as possible. And well, a computation that takes a long time should do so because it's hard, not because we don't want to work efficiently. And modular exponentiation arises very frequently in encryption. And so we naturally want to do that as fast as is possible. And well, okay, so let's be realistic here. It would not be the end of the world if my order at tchotchke.com would take 5 milliseconds to encode rather than 1 microsecond. However, markets also run on these things, and this is something where I have very little direct knowledge, but I talked to a guy who actually works as a trader, is a mathematician who works in the private sector, and he told me that secure bulk trades must take a short time for individual transactions, because even when you're trading a million share, keeping track of things is happening on a per share basis. And even if it doesn't, there are large numbers of trades where you trade shares from different companies, which are all individual transactions. And I think that is the key here, individual transactions. And there may be billions of individual transactions, and so all of a sudden, when you're looking at, let's say, if you're looking at something that takes on the order of milliseconds, then a billion transactions would take 5,000 seconds, and that's slow based on the market, right? However, if they all take 1 microsecond, then a billion of transactions takes only 1 second, and that is something that the market can live with. So there is a distinct interest in making these operations as fast as possible, not just on a research level, but really just based on the fact that things sometimes happen in such large bulk. And so that means we want to compute, if we have a base b, an exponent n, and a modulus m, where the base is, of course, smaller than the modulus. When we want to compute the least positive residue of b to the n modulo m, which would be the result of exponentiation modulo m, then this theorem says that this residue can be computed using on the order of O to the log 2 of m squared times log 2 of n bit operations. It turns out the argument we're going to give will work whether we go modulo m or not, but certainly then the modulo m cuts things down because otherwise numbers get arbitrarily large, and so this log would get a little bit larger here too. Okay, so the proof is we're going to find a k so that 2 to the k is smaller or equal than n, which in turn is strictly smaller than 2 to the k plus 1. And that takes capital O of log 2 of n bit operations, because you just compare powers of 2 to n until you bust through the ceiling here, I guess. And then you compute the least positive residues of b squared, b to the 4th, up to b to the 2 to the k by squaring and reducing. And that takes capital O of log 2m squared log 2n bit operations. Log 2n because you have to do it these k times, and log 2m squared is what the squaring and reducing takes. And then you piece together b to the n from there by multiplying and of course reducing modulo m, the residues of the b to the 2 to the j, for which the j's binary digit of n is equal to 1. And yeah, that takes capital O of log 2m squared times log 2n bit operations, again because you're multiplying log 2n times. And well, that is the proof. Okay, so what have we done here? We have built an arsenal of tools for arithmetic modulo m. That arsenal is the typical way in which sometimes in discrete math we build an arsenal, which means somebody, in this case the author of our textbook, has put together some tools that we just need to refer to later on, and we've just put them all out there. We've had some actual applications already with the fast modular exponentiation. We have also seen, and the big part here is, we have seen that arithmetic modulo m works. The equivalent modulo m sign really does work like an equal sign. We have seen that we can cancel numbers in arithmetic modulo m as long as those numbers don't have any common divisors with the modulus, which is a very, very fundamental result for this kind of arithmetic. And we will now, in the next presentation, start using this arithmetic to solve certain kinds of equations and to represent large numbers using the Chinese remainder theorem. I'll see you there. Thank you.